Hello, everyone. My name is Brad Williams, and today I'm going to present some information we have on our pre-production runs covering visible metalenses up into the near IR range. Going too far into the presentation, I wanted to take a second to highlight some of the other collaboration work we're doing in this meta-optic arena. Here's some various different papers, and here's their IDs. Some objectives, first of all, is to go over our Moxtek Metalens production. With us being able to run high volume production, we have some advantages in our development process. So I'd like to hit on some of those. Cover some key learnings from running high volume pre-production runs and some data we were able to gather and analyze and compare and contrast. And then I wanted to hit a point where NIL can achieve a higher absolute focusing efficiency than the typical TPUV litho, depending on the structure sizes and how small structures you can make, and then cover some of Moxtek's capabilities and some advantages. So first, to start off, let's talk about a Moxtek Metalens production line. Just a basic overview. Moxtek is headquartered in Orem, Utah. We have two business units. We have an optics business unit and an X-ray business unit. And you can maybe see in this this map here, you can see that we have optics fabs here, and then our X-ray production goes on in these fabs. Next, I wanted to just hit on some basic comments on metasurfaces and our capabilities. With this slide, we were able to show our wire group polarizers. They're really metasurfaces also. And then you can make all kinds of crazy looking metasurfaces to do different things with the light, like dot projection, or this is an example of like a focusing lens. Or we have these test structures that are beam diffractors that diffract it all into one set angle. This structure is actually really good for measuring focusing efficiency because it's easy to capture all light at one angle, and you can measure how much light makes it to that angle. And you can easily measure your zero or linkage. Anyway, our capabilities, you can see here we got high volume manufacturing with imprint and etching and deposition. Well, the next point I wanted to hit on is the advantages in developing in a high volume manufacturing facility. So Moxtek's Metalens pre-production line, we have gone through and made many different kinds of masters, as you can see all the various layouts here. From those masters, we've made many thousands of wafers, all different varieties, anywhere from a few lenses on a shuttle to a full production, over 1,000 lenses on the wafer. And then we also measure performance. So here's like a full year's worth of baseline performance data, and you can see, we've trended that over a whole year. Each one of these data points is a lot with multiple wafers and lenses per lot. This being able to have a trend shows how easy it is to track a significant change, like this change where we measure filter. We did some improvement in our measure step by adding a narrower band filter. And we've produced many different kinds of lenses. This graphic is to show you all the different lens diameters we've made. We've made lenses on a whole number of different wavelengths and a variety of different focal lengths. Next, I'm going to talk about how you can evaluate lens performance with a large sample size to get statistical significance. And in this volume production, it's very easy to change some different parameters and to characterize how they impact the performance. So if you take a typical lens with these specific parameters, a green lens, focal length at 5 or 2.5, 1 millimeter diameter. If you're in a research lab, you can make a few of these lenses. We can make hundreds of them and easily run very different conditions, such as different pillar heights or different sidewall profiles, or even vary the CD bias and collect enough data to have a significant comparison between how all these are impacted. So using those kind of tools and that kind of information, we have some key learnings we were able to discuss that we've been able to run focused experiments around. And the first one, just to give you the punchline up front, is MTF is very stable, minimally impacted. And absolute focusing efficiency has measurable impacts from processing and design. And metasurfaces are minimally impacted by defects. So on this slide, you can see various lots that had different processing conditions throughout the different runs. And this is our focusing efficiency. On all these tests, we're going to use the same test lens. It's a 1 millimeter diameter lens, 532 wavelength, 0.1961 NA. Anyway, you can run all these different processing conditions, and you can see how the focusing efficiency varies. You know, how we're able to take some lower efficiency and make it better. Then if you compare these exact same lenses with the MTF has hardly changed. It just is pretty much rock solid. We only had a few different things that happened down here that were able to change the MTF. So that's a significant understanding, and that's pretty key. So that whole group of MTF is a standard deviation of 0.3%. Basically, the results are like I already said. You know, your focusing efficiency can go up and down, but your MTF is pretty much rock solid. So in this test, this comparison, use that same lens. We have two different design methods. Your conventional design method, you see most of the publications, most of the design softwares, you know, design like in the conventional method. Moxtek, we've come up with a method to improve efficiency and a better design, improve processing performance. And using that same lens and comparing these two, there's a significant difference in design. Over here, you know, MTF is still not as heavily impacted, but it's enough to almost, you know, enough to make it significant. But that's a great improvement by using our proprietary designs. And then when you have a nice stable baseline, you can find wafer uniformity issues quite easily. You can see here, these three sites are all pretty much overlapping. They're not statistically different. And then if you look at these two edge sites, they are statistically different. And so you can use this to troubleshoot your process. Then we had a fortunate accident where on this one we were able to look at defects. So this lens on our master had a lens written here, and it's the same lens as our test lens I've been using for all this data set. And then we had another structure that we wrote over top, unintentionally, we wrote it over top of this lens. So this is kind of unique because if you take that area of defect, it's approximately 16% area of the lens. So the whole lens area, you know, versus the defective area. And we still built this lens and we measured it and we got data on it. And so look at this chart over here on the side, you know, our focusing efficiency. So this is the lens that has these defects. These two lenses don't. So it's clearly almost 14% different reduction in focusing efficiency for this defect. And then if you look at MTF, it has a similar impact, 13% or so. So if you compare the data, you know, assuming it's linear, you know, less than a 5% defected area is kind of a minimal impact on focusing efficiency in MTF. Anyway, okay, let's go on to the next topic. So we're looking at NIL compared to DPUV. So NIL can make smaller structures than DPUV lithography. So we wanted to see how that impacted performance. So to evaluate this, the background is DPUV has a hard time resolving these small pillars with wide spaces next to large pillars with narrow spaces. So NIL can resolve these very easily. And then by doing that, you can utilize a much smaller meta-optic design rules compared to DPUV. So this is an example of a drawn layout of a visible meta-optic where you have, rather large pillars close together and small pillars far apart. But NIL can easily resolve this kind of a structure. So the objective was, can the smaller structures that we can build with NIL make a better NIR lens than a DPUV design rules? So we designed the same we designed the same lens using DPUV meta-atoms versus NIL meta-atoms. We built both lenses on the same master, processed them using NIL, but DPUV meta-atom library had larger structures. Then we measured the performance from both of them to evaluate. So the concept is, if you're trying to match a phase profile and you don't have as small as steps to match that phase profile, you're not going to get as good a performance. So this is like an example if you're using larger design rules such as a DPUV. If you have the smaller steps that you can achieve with NIL with the smaller structures, you should get a better phase profile. So you can compare this. So to get your operating wavelengths, you have to get a smaller and smaller pitch to get down here in the visible range. So what if you made like an NIR 920 lens with these small meta-atoms? So this is what we did. So here's our lens specifications. We designed it for 920 nanometers. It's a 4mm lens and 10mm focal length. And here's the difference in the design rules compared to DPUV and NIL. These DPUV design rules we got from the most latest publication, talked about their best DPUV they could make a Metalens with. And so we took these design rules and we designed the lens. Then we ran it, built it, measured it, performance comparison is right here. So this is the focusing efficiency difference. And the NIL data is significantly different, and the efficiency is 11% better than the DPUV. Then if you compare the MTF, they practically overlap. So the results are NIL can accomplish a much smaller meta-atom library, and then make a better performing meta-optic. So then the last thing I want to hit on is some capabilities from Moxtek. Capabilities of building multiple onboard devices, and then a really good advantage of meta optics is an off-axis imaging. So we have some data on that too. So the visible off-axis image demo we built was for the red wavelength. And here's kind of an example of what it would look like. Like this is, say this was your eyeball, and this is the camera, and you don't want the camera right in front of your eyeball, so you have to image it from off-axis. We worked with ANSYS, they did the design for us. So this is the layout of what the design would look like. You'd have a meta surface on both sides of this, your sensor, and then your image and off-axis here to the eyeball, such as this. So this is what a simulated image would look like. And if you compare this to what it would take to do this same kind of thing with conventional lenses, it's much larger than a meta lens. You'd have to have multiple lens devices here, all stacked together, and then comparing the simulated image, you can see the advantages. So we built this demo, built double-sided, meta optics on both sides of the substrate. And then here's our results. So here's the simulated from the other slide, and then here's what the actual image looks from our device. All right, other capabilities. Is a really unique thing that we can do is say you have multiple optics devices that you need to build one on a plate, then you need to glue it onto a top of another thing. You build a filter, you build a quarter wave plate, you build a polarizer, you build a meta surface or whatever, you stack them, end up stacking multiple devices in your optical system. We can build all these devices together on one substrate. Or you can take that same concept and build it in an array of sorts. Like a color filter array or all kinds of various different things. So now in conclusion, I'm going to just hit the high points. Basically, Moxtek has established a volume production line for metalenses. We're releasing visible lens kit wafers as we speak for R&D and evaluation. We can come up with a comprehensive understanding of the lens performance. We're not just making a few of them and testing them and saying, well, we did great work. We're making many hundreds and thousands of them, and we can track performance baseline. We can see when something's different. We can get statistical significance between the data sets. Another big important thing to hit on is MTF is pretty much rock solid on these metalenses. Focusing efficiency, kind of is more significant, goes up and down depending on defects or processing, or even the way you design your metasurface. But MTF is pretty much solid, so that's a key point. The other thing is NIL can provide the smallest design rules to increase your focusing efficiency and your performance. So even though you're wanting to make a IR lens that you can function, using deep UV or some other litho method, to make it perform as efficient as possible, you need to have these smaller metaatom libraries. And the last thing I'm going to hit on is Moxtek can build all these components, multiple components on board the same substrate. Anyway, thanks for your time, and hope you learned something. Just as a wrap up, to touch again, here's our other projects we're collaborating with. If you're interested in more details on any specific topic, you can get the information at those papers. Also, the last point is, if you need to contact us, you can come visit our booths at any of our conferences we're attending. You can go to our website. You can click on this QR code, take you to the website. A lot of times at our booths, we'll have some demos where we put our metalenses on the iPhone just to see that they actually do focus in the visible range. They do pretty good. Anyway, you can get more information if you'd like.